In this second part of the presentation, we're going to look at special types of graphs. Now, in the first instance here, what we have is a picture of figures of four simple complete graphs. So each with the respective amount of vertices 1, 2, 3, and 4. First off, it's a simple graph because between each pair of vertices there is only one edge. I'll just give a quick example of a scenario where there is which is not a simple graph. If suppose we have two vertices like that, and suppose there is two different edges between them. In that case, that will be not simple. Okay. So in each of these cases, between each pair of vertices, there's only one edge. Okay. Now it's a complete graph because between each pair of vertices, there is an edge. They are all directly connected. They are all adjacent to each other in terms of the graph. So down here we have four vertices. On K4, there's no vertex in the middle, by the way, and they are all connected to each other. So this is vertex 1. Suppose it's connected to vertex 2 by that edge, vertex 3 by that edge, and vertex 4 by that edge. And likewise for vertices 2, 3, and 4. So that is a complete graph. That's the idea of a complete graph. What we're going to do here is, oops, I went too far. Let me scroll back up. What we're going to do here is we are going to draw K5. So this is an edge, a graph with 5 vertices. So let's first off draw our vertices. 1, 2, 3, 4, and 5. Now, between each pair of vertices, we draw an edge. So, I have that one there, I have one there, I have one there, 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 and lastly there. Okay, so this is a K5. Between each pair of the vertices we have an edge. Now consider the graph on the next slide. Let's actually just show you that for a second. There it is there. Just notice one thing, that it's split into two groups. We have A and B, group A up here and group B down here. And in group A, the vertices are connected to each vertex in group B and vice versa. But they're not connected to each other. For example, something that is missing is an edge from there to there, and an edge from there to there, and an edge from there to there, and something like that. Okay? It's not a complete graph. So it's not a complete graph because it is true that every vertex is adjacent to every other vertex. However, they are divided into two disjoint groups. So as I had it there earlier, 1 and 2 and 3, 4, and 5, A and B. So such that any two vertices chosen from the same set are not adjacent, they're not connected, but any two vertices chosen one from each set are adjacent, they are connected. In that case, we call that a bipartite complete graph. Okay, so every element in group A, or for each element in group A, is connected with every element in group B, and so on. So a formal definition: a graph is a bipartite complete graph if its vertices can be partitioned into two disjoint, non-empty sets, V1 and V2, or A and B as I had it earlier, such that two vertices x and y are adjacent if and only if x is an element of V1 and Y is an element of V2. So if basically they're in two different groups, two different sets. If the cardinality of group 1, V1, is M, and the cardinality of set 2, group 2, is N, we would denote it as KMN. So what we just seen there previously was a graph which we would denote K, 2, and 3. So a little exercise here, draw K, 3, and 3. So up top we will have the first group 1, 2, and 3. Down below we'll have the second group, and we'll denote them 4, 5, and 6. And we'll draw in the edges in green. So 1 is connected to 4, 1 is connected to 5, and 1 is connected to 6. 2 is connected to 4, 2 is connected to 5, 2 is connected to 6, and 3 is connected to 4, to 5, and to 6. So that is K, 3, and 3.